In the last part of Chapter 11, we'll look at tying together all of the individual gas laws that we looked at in the previous section to make something known as the ideal gas law. We'll look at the idea of what happens when you mix different gases and partial pressures, and we'll look at the stoichiometry of gases and chemical reactions. So if we take the three laws that we looked at in the previous section, Boyle's, Charles, and Avogadro's law, we can take those relationships, the inverse relationship of volume to pressure, the direct relationship of volume to temperature, and the direct relationship of volume to the number of moles, and combine them together. Notice it's because they're all proportional in some way to volume. So volume is sort of our factor that we're going to use to relate those. So volume is proportional to number of moles times temperature divided by pressure. We just took those three laws and kind of mashed them together. Now notice that we don't say they're equal, we say that they're proportional to one another. To set them equal, we have to have that proportionality factor or proportionality constant, and that's known as the ideal gas constant, which is represented by capital R. That is a constant number that allows us to equate them and set them equal. Now, if we look at this relationship, volume is equal to the proportionality constant R times the number of moles of gas times the temperature of the gas divided by the pressure. If we multiply both sides by pressure, we can neaten this up a little, and we end up with the ideal gas law, which is pressure times volume is equal to number of moles times the proportionality constant or ideal gas constant R times the temperature. PV equals nRT. So this constant, this proportionality constant R that we're talking about, what is that? Well, the number varies depending on the units, but the most common units for this factor, volume is generally in liters, pressure is in atmospheres, number of particles is in moles, and temperature must be in Kelvin. So we will use the unit of liter atmosphere per mole Kelvin. The number then for R in that case is 0.0821. Now, using this ideal gas constant requires us to use the units that are shown here. So if you're going to use the ideal gas law, the first thing you have to do, if your units are anything besides atmosphere, liters, moles, or kelvins, you must convert it to those units before you use ideal gas law. If you convert to those units, you're good to go. You are golden. Table 11.2 in your book shows the relationship between the simple gas laws and the ideal gas law, how you can boil it down. So if you're going to start with PV equals nRT, how do you know then what to do to convert it to another format? And that's all it's showing you here. But again, all you have to do is set it up. Now, again, remember in the other proportionalities, so if we had that pressure was inversely related to the volume, so 1 over the volume. When we combine them together, if I, multiply both sides by volume here, I get pressure times volume is proportional. So that's where the pressure times the volume, 1 equals 2, comes from in that case. So if I start with PV equals nRT, if the two sides are equal, then I should be able to divide both sides and not change the factor. So this becomes just 1, and this is, if PV is equal to nRT, this one is also 1. So what I can do is set it up where the pressure of the initial condition times the volume of the initial condition times the number of moles of the initial condition times R, which is a constant, times the initial temperature is equal to whatever I'm changing it to, P2. Those are supposed to be 2's. They look like equals. Let me see if I can make them look a little more like 2's. Number of moles for the second condition, R is a constant, and the temperature of the second condition. If I set those equal, so everything from the first case is equal to everything from the second case, and then get rid of anything that's constant. If the number of moles is constant, I can get rid of it. If the temperature is constant, I can get rid of it. So you can see how it boils down to each of the simple laws if I just get rid of whatever's constant. Or I can put all of those in there, change them all together. So in this example, we are given a gas with 0.845 moles, nitrogen gas, pressure is 1.37 atmosphere, temperature is 315 Kelvin, and I want to know the volume. What is the volume? Okay, first thing I do, I check my units. I need moles, I have moles. I need atmospheres, I have atmospheres. I need Kelvin, I have Kelvin, and I have the constant R. So I can find volume, and I just need to know that volume then is going to be in liters. So I can set it up, PV equals nRT, solve for volume right here, plug in the numbers, and I find that the volume of this gas would be 16 liters. Now, what if I don't have the units that I need to start with? Let's say in this case, I'm told the mass of the sample of gas, not the number of moles. It has a mass of 0.136 grams, a volume of 0.112 liters, a temperature of 298 Kelvin, and a pressure of 1.06 atmospheres. Okay, and I know the constant. Okay, so what I'm trying to do here is find the molar mass of this compound. Okay, well now what I'm going to have to do here is hold off on this mass for a minute. I'm going to kick that out, and I can see that I have a volume in liters, I have a temperature in Kelvin, I have a pressure in atmospheres, and I have R. I can use these pieces of information to find the number of moles, N. If I know the number of moles and I know the mass, keep in mind molar mass is just the mass divided by the number of moles, so it's just grams divided by moles. I've been given the grams, okay, so I just have to divide by the number of moles. All right, so starting with the ideal gas law, I solve for N, number of moles, plug in everything, making sure the units are correct, and I find that I have this many moles of gas. Now, if I take the original 1.36 grams and divide it by that number of moles, I find the molar mass of the gas. It's 28.0 grams per mole for that gas. By definition, what we've been looking at, the gases we've been looking at, are what we call ideal gases. It's in the very definition of the name of the law we just looked at, the ideal gas law. Well, why do we say ideal gas law? Why don't we just say gas law? Well, that's because gases don't always act ideally according to the kinetic molecular theory. Kinetic molecular theory says that particle size is small compared to the space between particles, therefore interactions between particles are insignificant. And ideal gases tend to be at high temperatures and low pressures. But we don't always have high temperature, we don't always have low pressure, and we don't always have insignificant interactions between particles. Okay, sometimes we have gases that are at relatively low temperatures or relatively high pressures, and we also have particles that just like to interact with each other. Sometimes, even though they have a lot of space between them, there's a polarity to the bond, or there's something that attracts them together. There may be significant interactions between particles. So these are what we call non-ideal gases. Now, what happens if you have a non-ideal gas? How do you account for that? Okay, so you have to account for it by looking at properties of that gas. They're going to behave just a little bit differently. But for the gases we're looking at, we will assume ideal conditions. Just be aware that if you start looking at gases under pressure or very cold gases or highly polarized particles in gases, those rules may not apply. But one thing you can look at is partial pressure, if you have a mixture of gases. Okay, now according to kinetic molecular theory, assuming ideal conditions, each of the components in a gas mixture is going to act on its own. Okay, so they're going to follow kind of that ideal condition, but if we have different gases, those different gases are going to behave according to the properties of that gas. Now, the pressure that comes from any individual component in a mixture of gases is called the partial pressure for that gas. That makes sense. You know, it's part of the mixture. It has a partial pressure. And you can measure the partial pressure for a particular type of gas, and that will indicate to you the degree of ideality or non-ideality of that gas. So is it an ideal gas, or is it not behaving as such? How much interaction of particles do you have? Okay. Now, the partial pressure of any given component is just that component's fractional composition. How much of the whole, what percent of the whole is that component times the total pressure of the mixture. So let's look at the most common mixture of gases that we know, the atmosphere around us, the air that we breathe. So the air in the atmosphere contains about 78% nitrogen, 21% oxygen, 0.9% argon, 0.04% carbon dioxide, a little bit of some other gases in amounts that will be insignificant to us. So if we have this composition for air, that means that each one of those gases is going to exert its own pressure on the gas. So for instance, the nitrogen molecules are going to exert 78% of whatever the total atmospheric pressure is, 78% of 1 atmosphere. Okay, and it's independent of whether or not the other gases are present or not. So it's not, if you took away the oxygen, suddenly they're going to, the nitrogen's going to exert more pressure. It exerts what it exerts. Oxygen, same thing, 21% of the total pressure. If it's 1 atmosphere, 21% of 1 atmosphere. So for partial pressures, you just want the fractional composition. So it's just the percent composition divided by 100. So 78% is just, and that's 78% is just going to be equal to 0.78. And this is not writing on the screen well at all. So my extreme apologies for that. I'm going to actually try, if the eraser will pop up here, try that again, see if we can get that to come in a little bit clearer there. All right, so 78% is going to be equal to 0.78. You're just taking the fraction of the whole. Once you have that fraction, you can multiply it by the total pressure from the gas to find out the partial pressure for that component. So if we look down here, if I have a gas mixture at 1 atmosphere of pressure, the pressure being exerted by, in this case, this one's a mixture of 80% helium and 20% neon. So 0.8 atmosphere coming from helium, 0.2 atmospheres coming from neon. In the air that we're breathing, 0.78 atmospheres. If I'm at 1 atmosphere of atmospheric pressure, 0.78 atmospheres of nitrogen and about 0.21 atmospheres for oxygen. Okay, that's all we're doing. We're just taking the fraction of the whole for each one of those. Now, Dalton's law of partial pressures states that the total pressure of any gas system is just the partial pressures added together. We just add them together. So for the air, we already said we have 0.78 atmospheres coming from nitrogen, 0.21 atmospheres coming from oxygen. Remember, argon was 1%, so 0.01. We could add in the carbon dioxide, which is fairly low, but essentially when you add it all up, you get the 1 atmosphere of pressure. Now, what if I don't have air at 1 atmosphere of pressure? What if it's something different? And what if I'm not in atmospheres? I'm in another pressure unit. Well, again, it's not like temperature where it has to be in Kelvin. As long as in pressure you have the same unit all the way through, you can still add them up. Just make sure that all the pressures have the same pressure unit. In this example, a mixture of helium, neon, and argon has been put together, and it has a total pressure of 558 millimeters of mercury. And then the partial pressure of the helium is 341 millimeters, neon is 112 millimeters of mercury. What is the partial pressure of the argon? It's very simple. The total pressure is equal to the sum of the partial pressures. So I have the total pressure, I have the pressure of the helium, and I have the pressure of the neon. So I just need to solve for the pressure of the argon. I just subtract the pressure of the helium and the neon from the total pressure, and I find that the argon is exerting a pressure of 105 millimeters of mercury. Now, this idea of partial pressures, again, is very important to us as human beings because our lungs have adapted to this idea of partial pressure, and in particular the partial pressure of oxygen. Our lungs have evolved to breathe oxygen at a partial pressure of around 0.21 atmospheres. That's what our lungs need in order to get that oxygen in and out and to get it to the cells where it needs to be. Now, keep in mind, partial pressure is related to the total pressure. So we're used to the partial pressure being around 0.21 atmospheres from a total of about 1 atmosphere. But if the total pressure decreases, so if you go to a high altitude, you climb a mountain, that changes the partial pressure as well. The partial pressure of oxygen decreases as you go up. So if you look at an extreme condition like the top of Mount Everest, the total pressure is 0.311 atmospheres of all gases. And so the partial pressure of oxygen drops to only about 0.065 atmospheres. If you're used to 0.2 atmospheres, you're dropping down to a fifth of the oxygen that you're used to there. And your cells don't get enough oxygen, and they start feeling the effects of that. So you have negative physiological effects called hypoxia. Hypoxia is simply oxygen starvation of your cells. Now, a mild case of hypoxia will cause dizziness, headache, shortness of breath, sometimes nausea, some other effects. But generally speaking, it really starts messing with you. Severe hypoxia, which will occur if the partial pressure of oxygen drops below 0.1 atmospheres, as it does on Mount Everest here, this 0.065, if that isn't monitored and taken care of, your cells basically starve for oxygen. You can fall unconscious, or you can basically asphyxiate. You die from lack of oxygen. So any climber hoping to make it to the top of Mount Everest is probably going to need to carry an oxygen tank. They're going to have bottles of oxygen in order to help them breathe to make it, especially since they're exerting energy and they're actually using more oxygen than they would normally. So it becomes very important to a climber to know about that partial pressure difference. Now, what if you go the other way? We've talked a little bit about scuba divers. Just like low oxygen levels have a negative effect, so do high oxygen levels. So if you increase the pressure, you go down to 30 meters. Remember, we said that the pressure there is around 3 or 4 atmospheres. So if you go to 4 atmospheres, partial pressure of oxygen goes up to 0.84 atmospheres. It's 4 times what you're used to on the surface. The increase in that pressure of oxygen causes a higher density of oxygen molecules to go into the lungs, forces more oxygen into the body tissues. And if it gets beyond about 1.4 atmospheres, it causes oxygen toxicity. So instead of your cells being starved for oxygen, they're being poisoned by the oxygen. There's too much. And this is characterized by twitching muscles, tunnel vision, and convulsions, and again can lead to death. If they go too deep without taking proper precautions to adjust the amount of oxygen, they actually, divers can drown because of that oxygen toxicity. Okay, so the surface, you have these partial pressures, increases as you go down to 30 meters. So big difference there. If you look at the concentration of oxygen in the lungs of the diver versus the person at the surface, you can see that massive increase in the concentration. So for climbers going to high altitude, it's pretty easy. You carry a tank of oxygen, you get a little more oxygen. What do you do if you're diving to a depth? You can't really stop breathing and stop taking in air. You still have to keep breathing in and out. So what do? Well, we need to just cut down on the partial pressure of the oxygen in there by taking out, number of moles of oxygen. We're going to change that up a little. Okay, so, and then nitrogen as well. Sorry, let's talk about the nitrogen level as too. So this is the idea of nitrogen narcosis, or the bends. That's from an increase in the partial pressure of the nitrogen we're breathing in. Okay, so if you increase the nitrogen concentration by going from a pressure on the surface, 0.78 atmospheres. If you're down at 30 meters, it increases 3.1 atmospheres. Okay, if you get beyond about 4 atmospheres of partial pressure of nitrogen, you end up with nitrogen narcosis, the bends. Divers describe it as feeling tipsy or drunk. Their judgment becomes impaired. Things start, they cease to make sense to them. They start doing things that seem really silly because their brains are not working quite right. All right, so they have the problem of oxygen toxicity and nitrogen narcosis at deep pressures. So deep sea divers adjust for these conditions by using different mixtures of gases. Now, one of the better known versions is something known as Heliox, and it's a mixture of helium and oxygen. And it has a smaller percent of oxygen than you would find in the air being breathed at the surface. It's less than the 21%. So you lower the risk of oxygen toxicity. As you increase the pressure, you get it up to about the same amount of oxygen that you're used to. The helium in there, you're replacing nitrogen with helium to eliminate the risk of nitrogen narcosis. So the helium has a very different effect at pressure than it would at the surface. If you breathe helium at atmospheric pressures, that you end up with the high squeaky voice and all that, but it's not good for your lungs at atmospheric pressure. It's not as harmful at deep pressure because of the difference. It's not being forced in. It changes that partial pressure. A good dive shop will help you calculate the best mixture for the depth of the dive. It depends on how deep you're going and how much pressure you're looking at as to what percentage of helium and oxygen you would need in that sample. Now, there are some examples of how you would calculate that. This is exactly what a diver would do. Let's say that the diver is going to 100 meters. So the pressure at 100 meters is going to be about 10 atmospheres. And they need a Heliox mixture that has 2% oxygen at that point. So what would be the partial pressure of the oxygen if they have 2% oxygen in their mixture? Okay, so percent oxygen, 2%, total pressure is 10 atmospheres. What is the partial pressure of oxygen? Remember that partial pressure of any component is simply the fraction of that component times the total pressure of the gas that you're looking at. All right, so in this case, the fractional composition, 2%, convert it to a fraction, it's 0.02. Multiply that by the total pressure of 10 atmospheres. We see that the partial pressure of oxygen in that mixture is going to be about 0.2 atmospheres, which is the partial pressure of oxygen that you would breathe normally on the surface if you were not diving. So that's what you're trying to do. You're trying to match that approximate 0.2 atmospheres if you're diving. All right, and then last thing to look at is the idea of stoichiometry. What happens if we have a reaction going on? So if we have gas being produced by a chemical reaction, such as the reaction of zinc with hydrochloric acid. If you drop a piece of zinc metal into hydrochloric acid, you get a single replacement reaction, produces zinc chloride dissolved in solution, and hydrogen gas. Now, if we take that hydrogen gas and instead of just letting it vent to the atmosphere, we bubble it through water, the water molecules become mixed with the gas molecules. The gas dissolves into the water, and we get a pressure of water vapor over the top of that solution that is a mixture of the pressure of the hydrogen gas and the pressure of the water vapor. Okay. So how could I find the partial pressure of the gas in that system? All right, and let's say we have an example where we collect hydrogen gas over water that has a total pressure, so this is the water vapor and the hydrogen gas, 758 millimeters of mercury, and this is at a temperature of 25 degrees Celsius. We want to know what is the partial pressure of just the hydrogen. Now there are tables that tell you partial pressure of water at a particular temperature. Okay, and that is this table 11.4 here. So we know we're at 25 degrees Celsius. So at 25 degrees Celsius, the pressure of the water vapor will be 23.8 millimeters of mercury. All right, so that's what this is right here. Now, the total pressure is just the pressure of the hydrogen gas and the pressure of the water vapor. We have the pressure of the water vapor from the table. They told us the total pressure, so all I need to do is solve for the partial pressure of the hydrogen. Very easy to do. Total pressure 758 minus the 23.8 partial pressure of the water vapor. So most of the pressure we can see is coming from the hydrogen gas, 734 millimeters. Now what if you want to look at the gas in relation to the rest of the components in the chemical reaction, such as the reaction of zinc with hydrochloric acid? Now if you have a reaction that involves either a gaseous reactant or a gaseous product, the amount of the gas is often going to be specified in terms of the volume at a given temperature and pressure. In order to use it in the balanced equation, in order to compare it stoichiometrically, remember, stoichiometric comparisons involve moles. So if you have a balanced chemical equation with a gas reaction, that's telling you you need to convert to moles. You use the ideal gas law to convert pressure, volume, and temperature, okay, and the constant here as well. Convert that to number of moles. Once you know the number of moles of gas, then you can use the stoichiometric coefficients from the balanced equation to convert other quantities in the chemical reaction to whatever you need. Okay, so here's the key right here. If you're looking at gases in a balanced equation, look, you're probably going to need to convert to number of moles. Here's an example. How many moles of ammonia would be formed by the complete reaction of 2.5 liters of hydrogen at 381 Kelvin and 1.32 atmospheres? Okay, so they were very nice and they gave us the units that we need: atmospheres, Kelvin, liters. And we're going to assume that we have an excess of nitrogen. So here's our formula right here. Hydrogen and nitrogen. Hydrogen is our limiting reactant. Nitrogen, we have plenty of those. How much ammonia can we make? All right, so what we have is all this information about hydrogen. Okay, but we need to know moles of ammonia. So that's telling me then the only way I can relate all this information about hydrogen to the ammonia that I want to know is to put it in terms of moles. So I have to find the number of moles of hydrogen. So if I solve for number of moles according to ideal gas law, it's going to be the pressure times the volume divided by the constant R, and then that number multiplied by the temperature in kelvins. So that's what has been done right here. Number of moles is given right here, 0.1055 moles of hydrogen gas. Okay, now I can take the number of moles of hydrogen gas and convert it to the number of moles of ammonia based on my stoichiometry. There are 3 moles of hydrogen for every 2 moles of ammonia. So what this tells me is, for the conditions that are given, I will produce 0.070 moles of ammonia gas. Okay, so if you want to use gas in a stoichiometric relationship, find number of moles first. There is one other aspect to dealing with molar volumes that we want to talk about, and that's the idea of a molar volume at what is known as standard temperature and pressure, or STP. So if I have 1 mole of any gas, doesn't matter what the gas is, 1 mole of gas that is at 0 degrees Celsius, which is 273 Kelvin, and 1 atmosphere of pressure, the volume of that gas will be 22.4 liters. And that's just slightly larger than the volume of a basketball. Okay, so if I have those conditions, I have 1 mole of gas, I have 0 degrees Celsius, and 1 atmosphere. Okay, that is known as STP. Now, that molar volume, that 22.4 liters, is for an ideal gas. Just be aware. But again, we're going to presume all the gases that we're using here are ideal gases, more or less. All right, so what that allows us to do is use that ratio as a conversion factor. If I'm told that I have STP conditions, then I already know for every mole, I know what the volume is going to be. I have that as a conversion factor. So if I have 1 mole of helium that's at STP, its volume is 22.4 liters. So that allows me to calculate the mass because I know the number of moles, I know it's helium, so 1 mole of helium is 4 grams. 1 mole of xenon at STP has a volume of 22.4 liters, but notice the difference in the mass. If you look at the molar mass of xenon in the periodic table, it's 131.3. So vastly different mass of gas between helium and xenon. The volume, though, is going to be the same if I have standard temperature conditions and standard pressure conditions, and I have 1 mole of both of those gases. So if we kind of tie all of these ideas together, let's look at an example of this. Calculate the number of liters of gas that form at STP. Okay, so I'm looking for liters. Standard temperature and pressure, that already tells me that I know the temperature. It's going to be 0 degrees Celsius or 273 Kelvin, and I know the pressure, 1 atmosphere. And they have given us now, it's not 1 mole. Moles has changed slightly. 0.879 moles of calcium carbonate break down to form calcium oxide and carbon dioxide gas. Okay, so what we want to know is what is the volume of that gas? How many liters of carbon dioxide am I going to form? So what I need to do, again, it's a molar relationship. I am given the number of moles of a solid, calcium carbonate, but I can relate them to the number of moles of gas from my balanced equation. There's 1 mole of carbon dioxide for every 1 mole of calcium carbonate, according to my balanced reaction. Okay, now I could go through all this other stuff. Notice I'm told STP. I don't need the temperature and the pressure. I don't need to put it in ideal gas. All I need is that relationship between number of moles and volume according to STP. I can now convert moles to volume. So when I carry that out, I find that 19.7 liters of carbon dioxide are being produced by that reaction. All right, so that wraps up Chapter 11, dealing with the relationships of gases and the use of gases in stoichiometric relationships. And tied to this, the next section that we'll look at is Chapter 12. Chapter 12 deals with solutions and I'm sorry, not solutions, but mixtures. So you're going to be looking at properties of liquids, evaporation, condensation, some other properties in there. That will tie in somewhat to gases, but the gases are a little bit more of a unique case.